Hey everybody, welcome back to this playlist on smooth manifolds, where the second topic of discussion is going to be coordinate charts. A coordinate chart, also known as a chart on a manifold, which is an abbreviation for topological manifold. At this point, that's all we're assuming, the most basic structure that a manifold can have. That coordinate chart is a pair u comma phi, where u is an open set on our manifold, right? It's in our topology of our manifold, and phi is a homeomorphism. So phi takes an open set from our manifold and maps it to an open set in Rn, right? This guy lives in the topology of Rn, and we know that phi is bijective and bicontinuous. I'm not going to define those things here. Those are math facts. So I've drawn a nice picture. So what is the coordinate chart? It's two things. It is some open set on our manifold, and this map that takes u down to Rn, and it spits out an open set. So this pair here is a coordinate chart. What do they look like? These things. So here I have an example. Consider S1, which I'm describing as the unit circle, and S1 is a topological manifold. I'm not going to prove it here. I will work with it in a later video, but if you're worried about that, that's an exercise for the viewer. Prove that S1, with this definition, right, a circle, is a topological manifold. So here it is, all points in the plane such that the sum of their squares is 1. Right? We've all seen circles before, and if you haven't, this is not the video for you. Now, let u be equal to the points in S1 such that their y component is greater than 0. I'm being a little sloppy with my notation, but we're adults, and I believe in you. I know you can follow along. Now, let phi be the map that takes a point on the circle and just gives us back the x component. And if we think about this open set, that is this arc of our circle. And so what does phi do to that? It just spits out the x component. You can think of it as just projecting it down onto the x-axis, which I haven't drawn here because S1 exists independent of any coordinate axis that we put on it. And that is an important idea about manifolds, that they exist independent of their coordinates, and we will discuss that more as the video series progresses. But what does phi do to that open set? It sends it to this open set in R1. It's going to map that open set right back up to the circle. What is its inverse? Well, I've discovered it right here. So it takes in our point x, and we want it to spit out a point on our circle, right? Take in x and spit out that point. Well, we need an x and a y component for this point on our manifold. Well, we know what the x component is, so we can just put it here, but what is the y component? I have this definition of what a circle is, so I can solve for y. Y is equal to the positive root and the negative root of this function here, but we choose the positive root because it's going to do what we want. In some sense, you start with this function and then find an open set that it behaves nicely with, which is how you come up with this open set in the beginning. So since phi and phi inverse are both continuous and bijective on their domains, right, we picked a nice domain where this function behaves well. Then phi is a homeomorphism. And we know that u, as described here, is in the topology of S1, right? This is certainly a subset of S1, but I haven't shown you that this is actually an open set of S1. I haven't shown you that it's in the topology of S1. I'm remembering that S1 is a subset of R2, so this subset of S1 is certainly a subset of R2. And from the subspace topology, if I was to sort of draw some open set kind of bubble going around this, and we looked at where that open set intersected S1, we would get this arc here. So by the subspace topology, this is indeed open on S1. So since this is an open set, and since this is a homeomorphism, together they make a chart on the circle. So hopefully that clarifies what a chart is to you guys. Thanks for watching.